All right. Hello, everyone. Welcome to the International Methods Colloquium. My name is Justin Essery. I'm an associate professor of politics and international affairs at Wake Forest University. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by Rice University and the National Science Foundation. The IMC is affiliated with the Society for Political Methodology, who hopes that you will support quantitative research in political science by joining. The membership fee is just $10 a year for graduate students. Excuse me. I will post a link to join the society in the Zoom webinar chat window after this introduction. This week's speaker is Korhan Kocak, a PhD candidate at Princeton University, presenting joint work with Scott Abramson and Asya Magazinik. The talk's entitled, What Do We Learn About Voter Preferences from Conjoint Experiments? Korhan's talk will last between 30 and 40 minutes, after which point we'll take questions from the audience. You can ask a question using the Zoom Q&A Zoom Q&A button that appears at the bottom of the webinar window. And you can ask questions at any time during the talk, but the questions will be held until the end of the presentation unless they're strictly clarifying. A link to the paper and slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I'll post those links right after we get started. And now I'd like to welcome Korhan Kocak to the IMC. Korhan, welcome.
Thank you, Justin, for the introduction. As the title suggests, this paper is about conjoint experiments. And if you've done political science at any point in the last 5 years or so, you must have seen conjoint experiments a lot because they're very popular because of their unbiased estimation of parameters of interest to us. But just to fix ideas and make sure we're all on the same page, what I'm talking about here are forced choice factorial experiments where features of profiles are randomly picked and respondents are asked to choose the one they prefer the most. So here's a screenshot from a very standard conjoint experiment where you can see that each row corresponds to a different attribute and its values are randomly generated. And once candidates are fully generated, then respondents are asked to choose which one they would vote for in an election, for example. And the target estimand in most of these papers is the average marginal component effect, or the AMCE, which is defined as the effect of varying a feature on the probability a profile is chosen, averaging over all other attributes. And the paper that introduced this estimand and the paper that popularized conjoint experiments in political science is this 2014 political analysis piece by Heinmüller, Hopkins, and Yamamoto. And just to give you a sense of how popular these experiments have become, according to Google Scholar, this paper, even though it's only 5 years old, has racked up more than 400 citations. When researchers run conjoint experiments and derive AMCEs, they often interpret them to make statements about aggregate preferences, to make statements such as respondents prefer candidates who have an Ivy League education, or voters do not prefer older politicians or celebrities and are indifferent with regard to dynastic ties and gender, or Americans express a pronounced preference for immigrants who are well educated, or voters and legislators, all else equal, prefer female to male candidates. Some researchers interpret these AMCEs also in the context of elections by referring to them as a difference in average vote margin or a percentage point change in the probability of winning an election. So, what researchers try to do here is to summarize some population preference. But what we want to argue in this paper is that it's very important to be very precise in uh, who we're referring to when we say respondents have this preference or voters do not prefer older politicians. So what I will show you today is that without additional assumptions on the distribution of preferences, a positive AMCE of x over x prime does not give us that a majority of respondents prefer x to x prime. It doesn't imply that all else equal, a randomly drawn voter will prefer X to X prime. And it does not imply that X will defeat X prime in most elections. And the way I will show you this is first, I will describe what the AMCE estimates using a simple but informative example. And then I'll take a step back and characterize the AMCE as a preference aggregation rule. I will relate it to social choice theory, which will give me some very powerful tools, which I will then use to provide analytical bounds on the proportion of people who prefer X to X prime as a function of the AMCE estimate, and also derive conditions under which the AMCE does correspond to a majority preference. So let me start with the example. The primitives of the example are going to be as follows. I'm going to assume that preferences over candidate profiles are constructed from two things. First, the rankings of features, that is, the researcher's quantities of interest. Do voters prefer males or females? And two, the weights assigned to different attributes. So, how much an individual cares about, say, party ID relative to gender. What do they pay attention the most? I'm going to be agnostic about the content of these preferences. I'm not going to impose anything about where these preferences are coming from. I'm only going to impose that individual rankings over features be complete and transitive. And I want to be clear that the imposition of these assumptions is not going to bring about the issues that I'm going to highlight. These issues exist nonetheless. These assumptions are just going to allow me to talk about them in an informative and hopefully helpful way. So let me start. What I'm going to do with this example is I'm going to reverse engineer the process through which a researcher who runs a conjoint experiment goes through. And to do that, I'm going to start with the quantities of interest, that is, the rankings of features. I'm going to assume there are 5 voters and 2 binary attributes in our conjoint experiment. It's the party ID, that's Democrat or Republican, and gender, male or female. And I'm going to assume that my 5 voters have the following preferences. Voters 1, 2, and 3 prefer males to females, and they prefer Republicans to Democrats, whereas voters 4 and 5 prefer females to males and Democrats to Republicans. As I said, in addition to rankings of features, I'm also going to need the weights of attributes. So I'm going to assume that voters 1, 2, and 3 place more weight on candidates' parties. That is, they care more about party than gender. Whereas voters 4 and 5 place more weight on candidates' genders. That is, they prioritize gender over party ID. And I'm going to highlight the more important attribute using this orange color. So now that I have individual rankings over features and the weights assigned to different attributes, I can aggregate them and talk about preference orderings over candidate profiles. And they're going to look like this. So here I have in each column a different voter, and I rank from the most preferred to the least preferred every possible unique candidate profile. And the way I construct this is as follows. Look at voter one. Voter one prefers males to females and Republicans to Democrats, meaning that his favorite candidate is going to be one that has both of the features that he likes, so a male Republican. Whereas he likes a female Democrat least of all because she has neither of the features that he likes. So I'm going to put that in the fourth place. When choosing between a female Republican versus a male Democrat, however, notice that both of these candidates have one of the features that voter one likes and one that he doesn't. This is where the weights are going to come into play. Because voter one cares more about party ID than gender, he's going to prioritize party ID and choose a female Republican, which has the preferred party but not the gender, over a male Democrat who has the preferred gender but not the party ID. So the full ranking of voter one is going to look like this. And voters 2 and 3 have the same preferences, so I can fill those in. Voter 4 prefers a female Democrat most of all and a male Republican the least. But because she also cares more about gender of the candidate, she's also going to prefer a female Republican over a male Democrat, and similarly for voter 5. So now I have every voter's full preference ranking over candidate profiles, which will allow me to look at hypothetical matchups between any pair of candidates. So, for example, we can look at a race between a male Republican and a female Republican. You can think of this maybe as a Republican primary race. I can look at this table from the previous slide and notice that voters 1, 2, and 3 rank the male Republican above a female Republican. So, in such a matchup, they would vote for the male Republican. Voters 4 and 5 prefer the female Republican. She's ranked above the male Republican, so they would vote for the female Republican instead. So this election between MR and FR would be resolved in favor of MR with 3 votes in favor and 2 votes for FR. And I can do this for every possible race and populate this entire table. And notice before I move on that in the 6 possible matchups, male candidates win 4 of the elections. And in the 4 elections between male and female candidates, male candidates win 3 of them. So being male in this population seems to be an advantage because males win more elections than females, which is intuitive because I constructed the example in such a way that a majority of voters prefer male candidates. So let's look at how the AMCE treats this population. And I'm going to calculate the AMCE of male using the method described in Proposition 3 of Heinmiller, Hopkins, and Yamamoto. And to do this, I'm going to define this new operator called y bar, which is going to give me its first argument's vote share in a race against its second argument. So y bar of MRMD will just give me MR's vote share against MD. And what I'm going to do with that is I'm going to subtract an otherwise identical candidate, but with a different gender, how that does against the very same opponent. So what's FR's vote share against MD? And I can grab these numbers from the previous table. I know MR gets 3 of the 5 votes against MD, and I know FR gets all 5 of the votes against MD. So I can write this down and take their difference. And then I can do the same thing against the next opponent, say FD. I can take those and put them in as well. And then I go over and exhaust all possible opponents. And after I've done that, I'm going to switch the party ID of the first argument and compare how MD does against opponents with how FD does against the same opponents. So I can populate this entire table, take all these differences, and then sum over these differences, which gives me minus 2 over 5, which after the proper normalization gives me an AMCE of being male of minus 1 over 15. So the AMCE of being male in this population is negative. But we know that a majority of voters have a strict preference for male candidates. And we also know that male candidates win most elections. So the AMCE tells us the exact opposite of the majority preference. And the reason it does that is because the AMCE combines the direction and strength of preferences, effectively overweighing the preference of the minority because they have a more intense preference. And this happened because I constructed this example in such a way that there is perfect correlation between prioritizing gender and having a preference for women. Those voters who prefer women care more intensely about gender, whereas those who prefer men don't care about gender that much. And even though this is a very extreme example, that such a correlation between preference direction and intensity can be seen from the ANAS surveys when this precise question is asked. Moreover, it's not just gender, such a correlation between having a certain preference and caring more intensely about this thing is everywhere in politics. In this ANAS survey, for the questions that we have, the intensity question, out of the 22 issues, 17 of them have very high correlation. And I also want to be clear that what I highlighted between the contradiction of between negative AMC of being male versus majority of voters preferring males is not a sampling issue. This is the case when we had infinite time and money and asked all the questions possible to all of the voters, exhausted all possible information that we could derive from this conjoint experiment. And we still had an estimate that shows the opposite of the majority preference. So the question then is, what does the AMCE tell us about preferences, if not the majority preference? What the AMCE does is to give us a literally average voter, or a voter with average preferences. But what we want to argue is that majorities are decided by median voters, not average voters. When we calculate the nominate scores, we look at the nominate score and not the average nominate score, because we know that averages are sensitive to outliers, whereas medians are not. Before I move on, I also want to highlight very quickly that the AMCE also violates the independence of irrelevant alternatives, meaning that even in the absence of interactions, the AMCE coefficient or estimate is sensitive to the questions or the attributes or the profiles included in an experiment. And I will show how this works in the context of our example. Going to have the same 5 voters with same preferences as before, but I'm going to suppose that the experimenter now includes a third feature. For simplicity, let's call it age, that can take 2 values, old or young. And I'm going to assume that voters 1, 2, and 3 don't care about age very much. It's the least important thing for them. Whereas voters 4 and 5 care about it very intensely, even more so than gender. And to reiterate, there's no interactions whatsoever. So if you prefer females to males, you prefer old females to old males and young females to young males. There's no interaction between different preferences between different features. But nonetheless, what I can show you is if we calculate the AMCE of male in this new example, then we get an estimate that's positive. So now the AMCE tells us that being male is good in this population. So by including a third feature, even though it doesn't interact, we flip the sign of AMCE of male. So what's the takeaway here? We saw that the AMCE may indicate the opposite of a majority preference, and it depends on the randomization scheme, even when there are no interactions. Now, let me take a step back and look at the broader picture of what we're trying to achieve here. What we're trying to do is we want to go from choices of individuals to make statements about aggregate preferences. Or we're trying to map individual preferences to aggregate preferences. In other words, we're looking for a preference aggregation. Luckily for us, there is a very large literature that's devoted to the study of social choice that we can tap into when we need and extract what's useful for us, which is what we did, and found that the AMCE is a preference aggregation rule that's related to the board account, a very well-known social choice rule in the social choice theory circles. And what this connection gives us is that the AMCE inherits some of the well-known properties of the border rule, specifically the violation of majority and IIA criteria. And furthermore, this connection I will exploit to place bounds on the proportion of people who prefer a feature as a function of the AMCE estimate. So this leads us to our first main result, that is, the border scores are proportional to AMCE. And I think it's useful to go through the proof of this, and I will. So here's a sketch. The way the border score is calculated is as follows. The border score assigns the last choice of a respondent a score of 0. It assigns their second to last choice a score of 1, and it goes on this way in an increasing sequence until it hits the top choice and gives that a score of k minus 1, where I use k to refer to the total number of profiles. Let's put that aside for a second and suppose we asked a respondent to make every pairwise comparison possible. This respondent will never pick the last choice because that's what being a last choice is. It will lose every pairwise comparison it's in, so it will be picked a grand total of 0 times. The second to last choice will win one pairwise comparison against the very last one and lose all the others, so it will be picked once. And we can continue this way until we get to the top choice, which will be picked against all the others. Since there are k minus 1 other profiles, it will be picked a total of k minus 1 times when all pairwise comparisons are made. Now notice that the left side of this frame looks very similar to the right side of this frame, which is the first observation that a candidate's border score is equal to the number of times that candidate is picked when every pairwise comparison is made. Now let me define a new object, the border score of a feature, which is going to be the sum of the border scores of all profiles that have that feature. So in the context of our example, the border score of female would be the sum of the border scores of a female Republican and a female Democrat. And since this is simple addition, the equality from before is going to continue to hold, that a feature's border score is going to equal the total number of times all the profiles with that feature are picked. And which means that if I just take a difference, this equality is also going to continue to hold. That is, the difference in the border scores of two features is going to equal to the difference in the total number of times all the profiles with those two features are picked. Now, let me do a quick revisit of our example, how we calculated the AMCE. This is the table that we used to calculate the AMCE of being male, where we compared each candidate with an identical candidate except for gender, how they did against the same opponent. So we took this difference in each row and then summed over all these differences to get the AMCE. Another way we could have gotten at the same result would be to sum over each of the columns. So look at all the times all male candidates are picked when every pairwise comparison is made, and subtract from that all the times all female candidates are picked when every pairwise comparison is made, and take the difference of these two sums and get at the exact same result, which we know is proportional to the AMC. It's equal to the AMC after some normalization, which just proves our result that the difference in the border scores of two features is just equal to the AMC estimate times some constant. So this connection is very powerful because we know a lot of things about the border rule from the social choice theory literature. We know that the border rule fails to indicate the majority preference. It violates the majority criterion. So this connection tells us why the AMCE may sometimes indicate the opposite of the majority preference. We also know that the border rule fails the independence of irrelevant alternatives criteria, which tells us why the AMCE is sensitive to the inclusion or exclusion of different attributes or profiles. So now I'm going to exploit this connection and place some analytical bounds on the proportion of people who prefer a feature as a function of the AMC estimate and the size of the experiment. And this is our second main result. That is, given an AMCE estimate, the fraction of people who prefer a feature T1 to another feature T0 lies in this interval. And I'm going to run through the proof of this because I think it's helpful. I'm going to do this for the lower bound. The proof for the upper bound is very similar. And the way this is going to work is very similar to how the example worked. Remember in the example, those who had the preference for females also cared very intensely about gender. I'm going to assume the same thing and take it to its extreme. I'm going to say that the respondents who prefer T1 give that attribute the highest possible weight, whereas those who prefer give it the lowest possible weight. This is going to maximize the Borda score of T1 for any given fraction of supporters. And it's going to lead to the minimum possible Borda score for T0. In fact, I can show that those who prefer T1 maximally give k over 2 squared more points to T1 than to T0, where k again refers to the total number of possible profiles, whereas those who prefer T0 minimally give k over 2 more points to T0 than T1. Now, I know this, and I know what the AMCE looks like from proposition 1, so I can just write this down. The AMCE is then proportional to the fraction who prefers T1 times k over 2 squared plus the fraction who prefers T0 times minus k over 2, which when inverted yields the lower bound that I showed in the previous slide. And even though I showed this for only for a binary attribute, this is easily generalizable to non-binary attributes as well. But let me show you what these bounds look like. So here is a binary attribute, an AMC estimate of 0.05. On the x-axis, I have the total number of possible profiles, k. And on the y-axis, I have the proportion who prefer the attribute. So what the line you see tells you is that if you have an AMC estimate of 0.05 on a binary attribute with an experiment with 4 possible profiles, this AMCE can be explained by anywhere from 35% to about 70% of people having a preference for this attribute. If you had a third binary attribute, so that there are 8 possible profiles, these bounds grow. And if you had another one, then an AMC of 0.05 can be explained by anywhere from 20% to 95% of people having this preference. And this is under the assumption that this estimate of 0.05 is very precisely estimated, that we're in asymptopia where we know the true value of the AMCE estimate. And these bounds keep growing when we add more and more attributes. If we had an AMCE that's as large as 0.17, then we know that for the smallest possible conjoint experiment with 4 possible profiles, then we have captured the majority preference. Then we know that a majority of people prefer this attribute. But if we had another or more profiles, then again, the lower bound crosses this threshold of 0.5, and we're in this world where we don't know if we're talking about a majority or a minority preference. Only if we have an AMCE that's as large as 0.25, then we can be certain that for any size of conjoint experiment, we have captured the majority preference, that our AMCE is pointing in the right direction of a majority preference. But that's only true for a binary attribute. We were talking about a ternary attribute, an attribute that can take 3 values, then even an AMCE as large as 0.25, we could not be certain that we captured the majority preference. So what we've done next is to look at some realistic values, some values that practically showed up in real life. So we applied our bounds to the 11 papers with conjoint experiments published in APSR, AJPS, or JOP in the last 3.5, 4 years. I want to be clear, most of these papers are not making statements about majority preference. We just want to see how our bounds look in practice. And what you can see is that out of those 11 papers, only two of them we can be confident have captured a majority preference. And what I want you to notice is that those are the two papers that have relatively low K, that is, relatively few possible profiles. And the tau here refers to the number of values that attribute of interest can take. So both of the AMC estimates that have captured the majority preference are on binary attributes. Okay, so a natural next question to ask is, when can the AMC capture a majority preference? And what we have shown is that if we're willing to assume that the preference weights and directions are uncorrelated, then we can be certain that the sign of the AMCE points towards the majority preference. And I'm going to walk through this very quickly because it follows very easily from the proof of proposition 2. When we suppose that preference weights are distributed identically across supporters and opponents, that is, preference direction and intensity are uncorrelated, then in expectation, each supporter of T1 gives as many more points to T1 than T0 as an opponent of T1 takes away from it, which means that if we call this difference, say, delta, we can just factor out this delta and just write that the AMCE must be proportional to the fraction who prefers T1 minus the fraction who prefers T0, meaning that the AMCE will be positive if and only if more people prefer T1 than T0. Okay, so what are some of the takeaways from today? The AMCE combines intensity and direction of preferences to give us an average voter, a voter with average preferences. But in many real life applications, we want to discern these two things. Say, if we have an estimate, a positive estimate on racism, we want to know if this is driven a small number of very racist people or a large number of mildly racist people, because knowing which of those two worlds we live in is going to inform not only future research, but the policy proposals that we want to come up with to respond. More specifically, if we're talking about elections and we want to capture electoral majorities, what this paper tells us is that we want to keep our attributes binary to the extent possible, and the total number of profiles included in the experiment low. But be mindful that even then, small effect sizes still won't be able to detect majorities. On the flip side of this, what the IIA violation tells us is that the external validity of our estimates requires the inclusion of all relevant attributes. Because we know by adding different attributes, we can flip the sign of an AMC estimate. So to be able to speak to the real world and claim that our results have external validity, we need to be confident that we have captured the actual model of behavior that people base their decisions on. I want to lay out some directions for future work, some of which we've already started working on. I think an obvious next step is to come up with methods that recover weights assigned to attributes, which would allow us to evaluate the homogeneous or uncorrelated weights assumptions, under which we know that the AMCE is a much more powerful tool. Another next step is to develop some approaches that decouple preference direction from intensity. For example, writing down a model of voting and estimating its parameters, and therefore uncovering some marginal willingness to pay between different attributes. And finally, I think what this project tells us is that the social choice theory literature can inform our understanding of empirical estimates and empirics more broadly. So I think there is some room for progress in that direction. Thank you very much.
Oh, there we go. All right. Thank you, Korhan, for that presentation. At this point, Korhan Kocak is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And I really want to focus on one particular question that I think is especially important given your presentation, which is what research designs are contraindicated for conjoint analysis by your findings, and what sorts of research designs are, I don't know, not contraindicated, or in other words, not going to be substantially affected by your findings?
So I think the answer to that question is every time we want to we care about whether this is a small minority with intense preferences or a large majority with milder preferences. Every time we want to discern these two things, the findings of this paper are relevant. So this might be elections, this might be public attitudes. Um, what this paper tells us is that there are conditions under which the AMCE estimate does correspond to a majority preference or any sort of threshold in the population, um, and there are conditions under which it doesn't. And it's up to researchers to decide where on this spectrum they lie.
So let me give you I think what represents a fairly typical example of where you might think about using conjoint analysis. I have a project where I'm interested in the extent to which voters respond to candidates' statements about human rights abuses. And the objective is to measure the marginal effect on voting behavior when a candidate from a certain party says something like, "Oh, here's my tax policy, here's my policy on immigration, or whatever. Oh, and by the way, I'm going to torture terrorism suspects." Right? You just sort of put that in there, and you're looking for the marginal effect. That there are a lot of experiments I think that use conjoint analysis that sort of go along those lines. Right? We're looking for the marginal effect of some sort of characteristic or policy valence or something on voting behavior. So what we actually did was just use a traditional experiment. But if I had done a conjoint experiment, how would your findings have changed my conclusions relative to the traditional experiment where I just randomly assigned just that one characteristic I'm interested in?
So it all comes down to interpretation. If your project sounds very interesting, by the way.
Oh, I'm sorry. I didn't mean to give a. I didn't mean to hijack your talk. It's
No, no,
something I've been
no.
thinking about.
I think that that's a very important question, and I'd like to chat about it afterwards if you have time. There are some other papers that work on a similar questions. So it mostly boils down to a question of interpretation. If we're talking about attitudes in a very abstract sense, then estimating AMCEs and saying people trade off these human rights issues versus different valence characteristics um, is very interesting. But if we want to talk about um, a proportion of voters or how much voters are willing to trade these things off, then it might be helpful to consider other methods like multinomial logic, for example. That's or some of the methods that we're working on right now and hopefully will be present soon that will be more directed towards disentangling this preference intensity and direction.
Um, so this is sort of related to follow-on work that's happened in this conjoint analysis, not a subfield, but sort of topic, Now people are trying to extend the framework to be able to, let's say, recover mediation, or actually, really, moderation is the right word. Moderating effects of other variables. So, for example, the link between characteristic X and and behavior Y is strengthened or weakened in the presence of context Z. How are those efforts going to be, or how should they be impacted by this finding that a small number of intense partisans or whatever are going to make the result look stronger than it really is in the majority?
Let me ask this first. Mm, Do these papers or projects have the context as attributes included in the analysis in the randomization scheme? Is
I,
that how they do it?
I'm not an expert in this area. I've just seen a talk or two at Palmeth and whatnot. I think so.
Mhm. So I would say that I think conjoint experiments are really one of the most widely used and obvious ways of looking at interactions. I don't know of any other popular survey methods that are directed at um, extracting how preferences for different things or preferences for things versus the context interact with one another. Um, so I think that's a good way for conjoint analysis to go. Um, but the implications of this paper are going to still be relevant in that context as well. It's it doesn't matter if we like subset to certain demographics or look at different interactions. This difference between an average and a median respondent is going to be relevant regardless.
Part of the sort of selling point or the advantage of conjoint analysis is that it's giving us a lot of information um, for a relatively simple design, in the sense that um, we don't have to necessarily examine every possible pair of characteristics simultaneously. We can just do a whole bunch of things that are randomly assigned, and then we can get the quantities of interest out of it. Um, I assume that if we were to do things, I guess you would call it the old fashioned way, right? If you were to randomly assign every pair that you were going to compare, and then get an estimate for each one of them, and then reconstruct a sort of average marginal effect of the characteristic in that case, you would get the right answer because you would know the weighting. Is that right?
Yeah, yeah. But that so the one of the obvious advantages or the things that are attractive about conjoint experiments is exactly what you highlighted, that it provides a very simple framework that allows the testing of multiple hypotheses. But what we're trying to say here is that that comes with a cost. And what you're referring to would be a more straightforward way of tackling these questions, and this is how we used to do things. But then the reason, one of the reasons why we moved to conjoints from then is obviously this testing of multiple hypotheses, but also the social desirability bias question. That I think one thing that conjoints are very good at is to deal with the social desirability bias question, where people would be um, not very eager to reveal their true preferences if the specific questions were very obviously targeted at extracting certain things like preferences over gender when it
Mm-hmm.
comes to politicians. Whereas conjoints are probably much better at dealing with this.
It's funny. I my intuition agrees with you, but I did a practice experiment in my undergraduate methods class the other day, and I thought it was going to be really obvious what I was looking for, and nobody did. I had to actually tell them what it was. So I don't know. I haven't done any systematic study of how well people are on picking up on what we're looking for, but
I agree with this. We also ran a conjoint of our own, and it went the exact opposite way of my intuition. So, don't trust my intuition.
Well, it looks like we don't have any questions from the audience, so I'm going to go ahead and thank Korhan Kocak for being our presenter this week. I want to remind the audience that the presentation will be posted to our website shortly after this broadcast if you'd like to share the presentation with someone else or watch it again later. I also want to invite our audience to join us on Friday, December 6th, so we're taking a week off for the American Thanksgiving. But a week after that, we'll host Moritz Marbach from ETH Zurich. Please visit our website, www.methods-colloquium.com, to get more information about this talk. Thanks for giving the talk today.
Thank you.
And I hope to see you all in 2 weeks.